So then, here's our next example. Okay. Ethanoyl chloride and ethanol. So this time we're keeping the acid chloride the same, and we'll do that for all these examples, but we've changed the nucleophile out from water to an alcohol. Pause the video, copy the structures, do 2 curly arrows. So then, there we go. There we go, exactly the same as the previous 2 examples. Working downwards. Here's your intermediate. It's starting to look a bit more complicated, but it's not really that bad, okay? We need to pause the video and draw on 3 more curly arrows. So we should have that, as we always do, that, as we always do. And then with the hydrogen, you might think, where am I supposed to put it? I'd probably do it like that, okay? I'm just avoiding putting it directly on the plus to show that I understand that it's hitting the oxygen. It's going on the oxygen because it's positive, but I'm just trying to avoid hitting the plus to make sure that my curly arrow head ends at the oxygen, if that makes sense. So then, this time I'm going to say pause the video and have a go at drawing the structure of the product rather than just scrolling down. So you should have had a go at that already, okay? And you should start to recognize it. Again, it's that thing of, you know, you could work out from a table of data what you're going to get, but actually, when you look at this, by now you should recognize that this makes it an ester. That's the ester kind of functional group, that bridge. And naming esters can be a little bit complicated, but the easiest way, I think, is to remember that that part is derived from the carboxylic acid, right? Well, the normal route of making an ester is a carboxylic acid and alcohol. Obviously that's not what we've done this time, but let's just imagine we have for naming. So that bit looks like the carboxylic acid, and that's the O8 part. There are 2 carbons. So ethanoate. This part comes from the alcohol. There are 2 carbons. So ethyl. Okay, ethyl ethanoate. We've got hydrogen chloride again. So again, just to reinforce what I said earlier, you could learn an acid chloride plus an alcohol gives you an ester, and that's fine, but you can work it out if you know the mechanism. So if you don't remember, you can still figure it out. Next example. Oh no, sorry, equations I should say. So there they are. Same idea. We've got the one for ethanoyl chloride and ethanol, and then we've got the one for any acid chloride and any alcohol. So next example. So things start to get a little bit more complicated here just because there's a bit of a wrinkle. You'll see what I mean in a minute. But for now, you know what to do. Pause the video, copy the structures, 2 curly arrows. So we should have that one, that one. This time, again, just to sort of ramp up the level of demand a little bit, I'm going to say pause the video and draw the structure of the intermediate. Don't worry about doing the arrows yet, but pause the video and draw the structure of the intermediate, and then we'll talk about the arrows. Okay, so we should have this. Again, it's that idea that the nucleophile always has too many bonds at this stage and therefore has a positive charge. So actually you can do the curly arrows here, it's just that there's an additional thing we have to think about. So we're going to have that, that, and then any one of these, but I'm going to choose the one on the left. Okay, and that's fine, the mechanism sort of stops there, but the wrinkle is to do with the fact that this is ammonia that we're using, okay? And this is one of the kind of problems with A-level chemistry, because they do this for ammonia, but they don't do it for the subsequent nucleophile. But anyway, let's have a look at what I mean. This might ring some vague memories from the nucleophilic substitution of ammonia with halogenoalkanes. You'll see what I mean in a minute. If there's an excess of ammonia around, right, So let's say there's some more ammonia molecules kicking about. Ammonia can act as a nucleophile, but it can also act as a base, okay? Now, what that means is that the hydrogen ion that's released here, okay, is probably going to get picked up by another ammonia molecule. And this is kind of a required part of the mechanism when you look at the nucleophilic substitution reaction. Again, it might be vague memory that, but it is something you do in year 12, okay? Now, the sort of twist here is, it's a weird thing. This does not need to be here in this mechanism. So just to be clear, the thing that I've just drawn, that I've highlighted in green, it's not required in this mechanism, but we have to talk about it because it is going to need to be reflected in the equation, which is kind of annoying, right? And it has an impact on the byproduct. So you'll see what I mean in a minute, okay? So we're saying basically that the hydrogen ion that's released, this one here, okay, it isn't going to be bonded directly to the chloride like it has been in the previous few examples. Instead, there's going to be something else that goes on, and we'll see what that looks like in a minute. And that's because ammonia can act as a nucleophile, like it did in this step, but it can also act as a base, like it is doing in this step. It's going to be a proton acceptor, a base. So, right, product, this time I'm not going to ask you to do it, I'm just going to say, here it is. We'll talk about the thing on the left, okay, and then we'll talk about the thing on the right. The thing on the left, you might not know how to name this, you might not even know what it is, all right? So let's talk first of all about what this is called. This class of molecule is called an amide. The way that we spot an amide is we look for this combination of elements bonded in this particular arrangement. A carbonyl group and an NH group. That's an amide. That's how you spot it. If you do biology, then you might well sort of recognise this as a peptide. And peptide is just a biochemist word for amide. They are basically the same thing. Obviously, a peptide has to be made from amino acids, right? So they're not exactly the same thing, but the peptide link is just an amide link. So, hopefully you've kind of made a note of the fact that that's how we spot this thing called an amide. Naming amides can get reasonably complicated. You'll see that in the next example, right? And it's an important part of the amines topic that we'll look at later on. For now, this amide's fairly simple. You put the suffix amide or amide on the end of the name, and then you use the root or the prefix according to the number of carbon atoms that are in the amide. So this one is called eth, because there are 2 carbons, anamide. So remember, 2 carbons, no carbon-carbon double bonds, molecule contains CONH, so it's an amide. Ethanamide, that's how you say it. Now, the other product, instead of being H plus Cl minus to make HCl, instead is NH4 plus Cl minus. Let's just kind of reflect on where that came from. We said before that although it doesn't really need to be there in the mech, there is another ammonia molecule hanging around picking up a proton, so that is where your NH4 plus comes from. Quick reminder that this thing here, NH4 plus, is called an ammonium ion. You usually first encounter this because it's a good example to introduce the concept of coordinate bonding in year 12, and you sometimes also do its shape, which is tetrahedral. So that's an ammonium ion, NH4 plus. Okay? So instead of having HCl, you will have NH4 plus, and Cl minus, you will have NH4Cl. This is a salt called ammonium chloride. That's the name of it. You may well have seen that just out of context as an ionic compound in any other kind of area of chemistry. So then, starting to get a bit more complicated, right? At any point, if you need to pause, rewind, check for explanations of things, you need to do that. So then, equations. This is why we have to kind of do this like strange version of the mechanism that has that extra detail in. When you write the equations, you have to reflect the fact that 2 moles of ammonia will react, okay? And you have to have the ammonium chloride as your other product. Like I said, there's an issue with this to do with how the A level treats amines as bases, but we won't worry about that just yet. So there's a bit of a twist, like I said, in this one, and it's just kind of something you have to get your head around and learn. So you've got the specific version and the generic version as usual. Right then, here's our last actual mechanism to look at before we do practice and stuff. Ethanoyl chloride and ethylamine. So this also crosses over with the amines topic, like the bit we just did with ammonia did. You know what to do. Pause, copy, 2 curly arrows. So then, ethylamine, which is kind of a related compound to ammonia, looks like that. It has a lone pair, so we're going to get movement that looks like that. Pause the video, have a go at drawing the intermediate. It's getting a bit bigger and bulkier, but have a go. Okay. So, here we are. We're going to have 3 arrows again. Same sort of idea as before. And annoyingly, it just kind of stops there for this one, which is like the first 2 examples, but not like the third example, because the third example had this weird scenario where there was another ammonia hanging around. In reality, that happens in this stage as well, because ethylamine is a base, right? And in fact, it's a stronger base than ammonia, so it's even more likely to happen. But like I said, for whatever reason, they don't expect it to be present in either mechanism, and actually with this one, it doesn't happen in the equations either. Although if you did do it the quote-unquote correct way, I'm sure the examiners would be okay with it. It's just I'm not going to include the detail because they don't ask for it. So then, pause the video and have a go at drawing the structure of your products. Again, there's some complications here, but have a go. So we should get these 2 things. We've got hydrogen chloride in this example. Like I said, there's a complication with how they do that, but for now, based on the information I gave you, that's what you should have come up with. The thing on the left, again, a bit tricky, this one, okay? So this, oh, I don't want that. That's better. This is an amide, like the previous thing, because it's got CONH, that's how you spot an amide. But it's a special class of amide because it has alkyl groups on either side of this amide link. You've got CH3C on the left hand side, you've got CH2CH3 on the right hand side. So this is a special class of amide called an N-substituted amide. That's the name of this class of molecule. What this is getting at is the N-substituted part basically means there's another hydrocarbon chain attached to the nitrogen. It's referring to this alkyl group here, okay, rather than there just being hydrogens attached to the nitrogen. The complication here is basically it makes naming them a little bit more complex, right? And the method for naming esters is going to come in handy again because it's a similar sort of principle, all right? So there are 2 parts to the name. You need to reflect one chain and you need to reflect the other chain. So let's start with the part that we kind of have an idea about, all right? In the previous example, just to go all the way back to that, we called this molecule ethanamide. Notice how there's no alkyl group attached here, it's just hydrogens on the nitrogen. So ethanamide. So in this molecule, we're still going to have ethanamide because we still have almost the same structure, there's a CH3, a CO, and an NH, but instead of there being a hydrogen attached to the right of the nitrogen, there's something else, right? And that's where the other part of the name comes in. But this part of it, the bit that starts with the carbonyl group and ends with the NH, is going to be ethanamide. So the next section starts with the prefix N hyphen, and the idea behind this part of the name is it's describing like that something is attached to the nitrogen. If we look at how many carbons there are attached to that nitrogen, there are 2. So if you saw this on its own, you would call it an ethyl group, which means the name has to be completed by saying N-ethyl ethanamide. It might not look like it, but actually what we're using here is a very similar logic to how we name esters, where one part of the name comes from the alcohol and the other part of the name comes from the carboxylic acid in most examples. And so you've got this kind of 2-part name that reflects 2 parts of the molecule, and it's exactly the same when you're doing N-substituted amides. Again, we'll come back to this later on in the amines topic. So, there's now a task to do, and it's first of all equations. So we've got different combinations of acid chlorides and different nucleophiles. You're to write an equation for the reaction using condensed structural formulae. For the ones that are marked with a blue asterisk, I also want you to name the products. So you can have a go at naming the others if you want, but I'm really only asking for the names of the products in 1, 2 and 5. And when I say name the products, I mean the organic products. Okay? So pause the video, there's plenty to go out there, so have a go. Right then, solutions. Okay, 1 through to 4, pause the video, check your answers. If you're kind of keen and you want to have a go at these, let me just very briefly, okay, this would be N-methyl propanamide. Okay, I'm not asking you to have done that, I'm just saying if you did have a crack, then that would be the correct answer. Okay, this one, number 4, would be, so that's just butanamide. Five and 6, we've got butyl methanoate in 5. And then finally number 6 was just equation, but again, if you've had a go, okay, that would be N-propyl ethanamide. So then, I hope you got on okay with those, alright? There's a lot of complexity in this kind of particular part of the carbonyl group topic, especially the bit that crosses over with the amines topic, which is something that we'll do later on. More practice. This time, mechanisms. Every single one is an acid chloride mechanism, because remember, you don't really have to do the mechanism with the acid anhydride. Pause the video, have a go. Alright, so once you're happy with your answers for those, you can pause video and check 1. Pause video and check 2. Pause video and check 3. Pause video and check 4. Quick reminder for 4. If you did this mech without that bit being there, that's okay. AQA don't require it to be there. However, the problem with you not doing it is you're less likely to remember how to write the equations properly, okay? Which is why we have to watch out. Pause, check 5. Pause, check 6. Didn't ask for names for anything here, and I'm not going to go through them, okay, because it was really just to test the mechanisms. Okay, that's it.